Alright, so guys, welcome to episode number 1 of the Resnick Halliday series. Throughout this series, we are going to be covering the theory as well as questions from Resnick Halliday. Now, we are only going to be solving the odd number questions and not the even one. First of all, why we are doing that is because if we do the even one as well, that increases the load by twice. And what I've noticed is throughout this book, more or less the questions seem to be similar in concept. So that would just waste our time. We need to learn something new over here. And today we're going to be starting off with vectors. I really don't know how long this is going to take, but I want to finish this all today. So let's actually get started and let's begin with vectors right now. Vectors is pretty important in general for physics, and this is how we build our fundamentals. Now, also, first thing, I'm really sorry for the background white noise that is coming. That's due to my fan. But anyways, okay, let's get started. Now, through our younger grades, we get to know that vectors are those quantities that that have a specific magnitude as well as a specific direction. Now, is this true? First of all, what do we mean by a quantity? A quantity is something that can be measured. When we talk about physical quantities, I'll just write PQ. When we talk about physical quantities, they're actually divided into two types. We have scalars and we have vectors. Now, we are told that the only difference between scalars and vectors is that vectors has direction, but scalars do not have directions. Now, we know that we are told that vector is anything that is said to have a direction and possess a magnitude, right? Now, let's talk about a special case. Let's talk about electric current. So, let's say there's this wire. We know that the electric current in this wire will flow from the positive to the negative, this way. Now, here, the electric current has a specific magnitude, and that magnitude is measured in amperes. We're going to be learning all of that. It's a pretty exciting series. And yeah, so we know that electric current is measured in amperes, and over here it has a specific direction, which means it is going from positive to negative, right? So is this a vector? Well, since I already mentioned that this is a special case, you would know that this isn't a vector. And why is this not a vector? Because it does not follow the triangle law or parallelogram law of vector addition. Now, I know you guys didn't understand what I mean by that. You don't really know what triangle law or parallelogram law is, or so I assume, right? So now we're going to be understanding everything from the very basics. Jim Quick says the best way to learn something is to empty the cup first. Forget all that you know about this and just try thinking of this as something new that you're approaching. Alright? So now, let's actually get started. So, where do we see vectors and why do we even need vectors? We know that sometimes it's important for us to convey both direction as well as magnitude. Let's say I'm over here at point A, and let's say there's a guy over here. This is my best friend. Okay, supposedly my best friend. Now, if I tell you walk 100 steps, right? Then you're just going to look at me pitifully. Why? Because I said something stupid. I said walk 100 steps. Did I mention which direction? I mean, it's pretty obvious that you would have to walk in this direction so that you reach over here. But that is just because you can see the point over here, right? So I'm also supposed to mention a direction. So I can either say that walk 100 steps, making an angle 30 degree from this line, whatever this reference line is. Or what I can say is, just let me change the color over here. Yeah. So, or what I can say is walk, let's say, walk 50 steps like this, and then walk 25 like this. Cool. Now I know that doesn't sum it up, okay? That's not even 100 steps. Alright, I get it. It does not follow the Pythagoras theorem, but this is just an example. Alright? So there are two ways in which you can reach his house. Let's forget the numbers. Otherwise I'll have to go into Pythagoras theorem and then I'll have to check for each one. Right? So either you can directly go from here to here, from point A to B, or you can take this right turn and then move upwards. You get it, the boring way. Alright, the longer way. So now this is why vector is important, because we need to specify directions. Now how do we represent a vector? First let's try and understand that. So as we know, a vector has a magnitude as well as a direction. We denote a vector by putting this arrow over it, or sometimes in more professional books you would see it has a dash. Now putting an arrow over the vector does not make it more professional. It's just a way of representation. All right. So if you see a letter and then if you see an arrow over it, in physics this means that this is a vector. All right. In physics this means that this is a vector. Now how do we represent a vector? So let's say we have a vector. We know that this a vector over here has some magnitude as well as some direction. Alright. So how do we calculate the magnitude? Just a second. I'm really sorry. Right. So how do we calculate the magnitude? Now to calculate the magnitude, it's pretty simple. What we do is we put this modulus. What is modulus? Modulus itself stands for magnitude. Alright. So if you guys would have learnt about it in maths, let me take you to the next slide. So if you guys would have learnt about it in maths, when you talk about magnitude of minus 3, mod of minus 3, modulus of minus 3, what is this? 3, right? Because we're talking about the magnitude over here. Irrespective of the sign, we really don't care, right? If I tell you that there's a point A, point B, alright, and now if I tell you that you have to walk 10 kilometers, I really don't care about anything else. I need to know what the distance is. So I have to walk 10 kilometers. I'm going to be like, no, I'm not doing it. It's that simple. Alright, so we don't really care about the sign. We just need to know the magnitude. Alright. Now that was a rough definition because I'm expecting these fundamental things to be known. So now this is how we calculate the magnitude of a vector. So let me give you another example. Again, I'm going to be using the same boring example, alright? So I know you guys would be tired of this and you wouldn't want to see another person giving this example ever again. So let's say we have 2 points A and B again, alright? Assume it to be whatever, maybe your girlfriend, maybe your crush, whatever, alright? So maybe that might bring some excitement into vectors. So now you have to go from A to B. Now what can happen is, I showed you earlier that there are two paths, two ways. Either you can take a right and then walk upwards, or you can directly walk to B. Now let's say that over here this is 100 steps, and let's say I'm not using Pythagoras, okay? Over here I won't be using Pythagoras theorem. Oh wait, should I? Nah, it's alright. Let's just assume, let's remove the numbers. Let's just assume this to be x. Alright, so I am traveling x distance. Alright, I'm traveling x distance from A to B when I'm going along this particular path. And I'm going to be traveling m distance to the right, n distance above, alright, to reach point B. Now what is the magnitude over here? Now you would notice that if I add this m plus n over here, that is actually greater than x. Now why? Alright, I will never left a statement unexplained. Alright, that's one thing that I have planned for this. I will never let anything that I say go unexplained. Now, why is this? This is actually the whole condition for a triangle to be formed, where the sum of any two sides has to be greater than the third one. Or you can actually even use this relation, since we are assuming this to be perpendicular because we are moving right and then we are moving straight up. What you can say is m square plus n square is equal to x square, right? Now if you take under root both sides, alright, now if you take under root both sides, you get x is equal to under root of m square plus n square, right? Now under root of m square plus n square, is it lesser or is it greater than m plus n? Is it lesser or is it greater? Let's take an example to figure out. Let's say we have this easy right angle triangle. So we have 5, 3 and 4. Alright, we know what this angle is going to be, but we won't name it. But alright, so even if you want to name it, you can just write 53 degrees. Alright, so now even though this is pointless, I would just remove it. Okay, so what do we have to find? We need to check whether under root m square plus n square, which is these two, whether under root 3 square plus 4 square is greater than or lesser than 3 plus 4. 3 plus 4 comes out to be 7. Under root 3 square plus 4 square comes out to be 5. So this clearly tells us that 7 is greater than 5, therefore m plus n is greater than under root m square plus n square for every condition. Now you guys might be wondering that these might be really small values and that's why it's working. But let me give you just one more example, alright? Let's say we have another right angle triangle over here. 13, 12 and 5, I guess. Yes, alright? So now, let's do the same thing again. Let's find under root m square plus n square. That's going to be 144 plus 25. That's going to be 13. And if we do 12 plus 5, that is 17. So we notice that in every single case, under root m square plus n square is lesser than m plus n in every single case that we have noticed so far. This is what's happening. And that is why, where did I go? Okay, that is why, wait, what is the point? I actually lost it. Okay, and yeah. So that is why. So my point actually over here was that since these are unequal, since I said that this was x and this was m and n, and now we know that m plus n is not equal to x, right? So which will we choose to be the magnitude? Should we choose x or should we choose m plus n? Now, the answer over here, and I'm pretty sure you guys figured it out. Let me just erase this. Now, what we do over here is to take the magnitude of a vector, we can first break it into its components. That's an easy way to understand that. Alright, so first let's continue talking about magnitude. The thing is, vector is actually that kind of a, it's actually a special kind of a chapter. And I wouldn't say it's a chapter, it's fundamental. So vector is so special that you need to know the upcoming part to prove the previous part, but you need to know the previous part to prove the upcoming part. So this is actually a little confusing for me to go ahead and explain, but I'm still trying. All right, so hopefully you guys are not getting bored. So right, so let's continue. So yes, where were we? Yes, how do you calculate the magnitude? To calculate the magnitude of this, what we do is calculate the hypotenuse. It's as simple. Why? Because vector has a specific direction. This might be a vector, this might be a vector, but these two together, it's not a vector. So this is the vector. This is known as the resultant vector. Alright? Actually, no, that's not the result. Actually, yeah, that is the resultant vector. Okay, so now that we know that, how are we going to calculate the magnitude of, let's say this? Let's say I have a vector that's going something like this. Alright, right now you don't have to worry about what's resultant vector. We'll be understanding that a little later. Right now just try understanding the concept of magnitude. Let's say this is let's say this is 6, this is 8. Alright, calculate the magnitude of this vector right over here. What's going to be, let's call this a vector. So what's the magnitude of this a vector right over here? Now what we do over here is use Pythagoras theorem. So we get 6 square plus 8 square, that is actually equal to 10, right? So the answer is 10. It's that simple. How did we do this? Let's try it again. Let's try another question. This time you guys try this. Alright, you guys try this in your mind. Now let's say I have just give me a second. Okay, right, 24, 10. What's going to come over here? Let's again call this a vector. What's the magnitude of a vector over here? Alright, the magnitude of a vector over here, again we will be using Pythagoras theorem. 24 square plus 10 square. 24 square is what? 576. What's 10 square? 100. And what is under root 676? 26 square. Is it? Maybe it is. So right, so that is going to be the magnitude of a vector. So a vector's magnitude is 26. So it's that simple. Alright, now we know the concept of magnitude. Now how do we figure out its direction? Alright, the best way to actually understand vectors is actually using the graph or using a Cartesian plane. Let me just go ahead and move to slide number 5. So let's say I have a Cartesian plane over here. Alright, Cartesian plane is nothing but just your xy plane. Alright, so yeah, let's say I have the Cartesian plane right over here. Now let's say I have a vector that's going somewhat like this. Let me change the color. Let me make this a little better. Alright, so okay, let's say that's a vector. Alright, now we can calculate its magnitude. How? It's pretty simple. What we're going to do is we're going to project. Alright, and let me teach you the concept of components also as well over here. Alright, so that will make it a lot simpler. So let's say I take a torch over here and I shine this parallel beam of light. Alright, I throw this parallel beam of light at it. Okay, this is a torch, even though it doesn't look like one, but just assume it to be one. So alright, let's assume this to be a torch, and this torch is shooting this parallel beam of light at this vector. Now there's going to be a shadow that's formed, right? And that shadow, will it be greater in length than the vector itself? No, right? The shadow is actually going to be this. It's going to be equal to its height. Similarly, what I do now is I shoot a light from here. Oh my god. Okay, so this is a torch, parallel beam of light. Alright, parallel beam of light. Now this time as well, its component turns out to be equal to its length. Alright, now this over here is called its x component, and this over here is called its y component. Right? Cool. So now we understood the concept of components. Now using these components, can we calculate the magnitude of this vector over here? Yes, we can. It's pretty simple. because we just have to use the Pythagoras theorem. So if we do under root x components square plus y components square, that will give us the magnitude of a vector. As simple as that. So now things have actually started to become clearer and clearer for you guys, right? Now you guys are actually understanding it. Now let's actually move on and let's see how can we add two vectors. Alright. Now how do we add vectors geometrically? Geometrically, cool, right? Sounds interesting. So let's say we take two vectors. Let's say we have a vector A over here. This is A vector. I have another vector B vector over here. Okay. Now, how do I add these two vectors? Now, if I say what's A vector plus B vector, does this make sense? Does it? Like, does it really? Because this 2 will be a vector, right? This 2 will be a vector. So what we do over here is we use some theorem known as the not parallel axis theorem, I'm really sorry, that's from rotation, Parallelogram Law and triangle law of vector addition. To add these two vectors, we use triangle law and parallelogram law. So how do we do it? Now, this blue color looks really bad at it. I apologize for it. Alright. Now what we do is we take, this is actually called the head of the vector, and this remaining portion is known as its tail. Alright. So what we do is we arrange it in such a way that the tail of one vector touches the head of the other vector. Cool? Now I have one interesting question, alright? This is important. Let's say I have a vector over here. Now let's say I took this a vector and in space itself I made another parallel one with equal magnitude and in the same direction. Alright, it's parallel. Okay, it's parallel having the same magnitude. Can I call this a vector as well? The answer is yes, I can, because it's free space. The free space has no defined coordinate system, and even if it did, if you shift a vector parallel, alright, if you shift a vector parallel, as long as it is parallel and you haven't changed its magnitude, that will still be the same vector. Because when are two vectors equal? When will a vector be equal to b vector? This condition will be satisfied only if the direction of the two is equal. Direction has to be equal, as well as the magnitude of the two vectors has to be equal as well. Now direction will be the same because first of all we have moved it parallel. So once we move it parallel, we know that the direction remains unchanged, and the magnitude, as long as you don't change the magnitude, is the same vector. So this is the same concept that we're going to be applying over here. So we shift a vector and we arrange the two vectors in such a way that the tail of one vector touches the head of the other. And once we do that, we have to join the tail of the vector to this head of this vector. Alright, let me repeat that again. When you have two vectors and you have to add them using this triangle law of vector addition, what we do is we arrange them in such a way that this tail of one vector touches the head of another vector. Alright, I think I changed. Yeah. So this tail of one vector touches the head of one vector. Alright. Now what we do is we join this tail of the vector to the head of this vector. And this what we have over here is known as the resultant vector. Alright. This is known as the resultant vector, and this is what the addition, this is what S vector is. Alright, this is what S vector is. Now using this we are going to be deriving a few things. Alright, and let's do that super quickly because I know that you guys are pretty good at geometry already. So let's say that I have a vector like this, alright, and I have b vector like this, and let's say I have, okay, let me actually make this simpler. So let me not, if they look like they have the same magnitude, then it would be too difficult for you to comprehend. So what I do over here is, right, now let's make the resultant vector. Okay, now what I do is I specify a few things. Let me call this angle theta, and let me just complete this right angle triangle. Alright, I'm completing this right angle triangle. So this over here is a right angle. Okay, this thing over here is a right angle. Let's assume this angle to be phi. Now let me just term these vectors. Let's call this a vector, let's call this b vector, let's call this r vector. Alright, that's the resultant vector. Alright, cool. Now let's actually derive a few things. What can we derive over here? Let's so let's call this x over here, and let's call this length y. What's y? This is y, this is x. How can we find a relation between x and y? Pretty simple, right? You can just write tan phi is equal to x by y. Now can we write that y by mod r vector is equal to cos phi, and similarly x by mod r vector is equal to sin phi? Can we write that? Yes, we can. So now let's transpose this mod r vector to this other side. What do we get? We get x is equal to mod r vector sin phi, and similarly if we do the same over here, then we get this y over here to be equal to mod r vector into cos phi. Alright, now I'm just teaching you how to do this because this will be important when we break things into components later in the series. So once we reach Newton's laws of motion, work, power, energy, rotation, and these mechanics chapters, we will be needing to break forces and different things into their components, and we're going to be doing that using this particular fundament. All right, this particular thing. So now what can we write over here? What can we write? Okay, but you know what, let's actually make this a little more interesting. This doesn't look fun enough. Let me make this a little more fun. And how am I going to do that? Let's say this is a vector, let's say this is b vector, and let's say this is r vector. Now this is what I call interesting things. So this is r vector, a vector. Okay, I shouldn't draw a vector over there, I'll tell you why. Okay, so a vector, let's say this is a vector. I mean, it really doesn't matter, I could have named this b vector. Let's call this b vector over here, this small one right over here. Let's call this angle over here theta, and let's convert this into a right angle triangle. This is the right angle, let's call this angle phi. Alright, so can I write this as mod b vector cos theta, and can I write this as mod b vector sin theta? Can I? Because we just did that. X and y were exactly that. So I did it. Alright, I named it. Now we can see this this right angle triangle. So let's just go ahead and apply the Pythagoras theorem, and we get mod r vectors square is equal to a mod a vector plus b vector cos theta square plus b vector sin theta square. Let's remove this square over here and let's put an under root. Now, how did this come? Alright, pretty simple. Look at the triangle. The side over here is a plus b cos theta, and this side over here is b mod b vector sin theta. Alright, we got this. Now what we are going to do is we are just going to expand, and you will see the relation that I wanted to derive. So, okay, blue wasn't a good color, right? Yellow. So we get mod r vector is equal to, on expanding that, we get, I'm just going to call this a square, alright? I won't keep writing mod and all. I'll just call this a. And similarly for b, for mod b vector, I'll just call it b, alright? So it will be a square plus cos square phi. Wait, did I write theta over there? Just give me a second. Alright, yeah, I'm crazy. It's not theta, it's going to be phi. So alright, even over here it's going to be phi. Thank God I noticed it, otherwise comment section would be filled with this itself. Alright, so this will be 2a cos phi plus b square sin square phi. Alright, now let me just see, did I do something wrong over here? Okay, it's 2ab. Alright, so okay, let me go ahead. Oh my god, I'm done with this. So it's going to be b square. It's b square cos phi, right? So this has to be b square cos square phi. So this is b square cos square phi. Alright, so now let's join them, and we know that's going to give us b square. Why? Because I can just take b square common, and then I have cos square phi plus sin square phi. I know this is going to be 1, so it's b square into 1, which is b square. Alright, so now these are the fundamental things. I won't be explaining them over and over again because that's going to just lead to a wastage of time. So we get that mod r vector is actually equal to a square plus b square plus 2ab cos phi. Alright, now don't write this as a plus b the whole square. Alright, there's cos phi as well. You have to keep that in mind as well. Alright, most of us, we get too excited when we see this, then we just charge at it. We don't care about anything else, we just charge at it, but we shouldn't do that. Alright, so now we understood what the triangle law of vector addition is. Okay, and we also know what components are and how all of that works. So I'm really sorry. So now we're going to be moving on to understand what unit vector is. Alright, now as I said, for any vector we need to talk about its direction as well as magnitude. Now the direction we have talked the magnitude we have talked about pretty well. Let's talk about the direction now. So how do we define a direction for a vector? So again, we're going to be moving to the Cartesian plane. So let's go ahead and make this Cartesian plane over here. And alright, let me make this vector. So now, to talk about the direction of this vector, what do I really need? I need to know this angle, right? I need to know this angle right over here, this angle. If I knew this angle, then I can talk about the direction, but I don't know the angle. What you can do over here is when you have a vector, and if you divide that with its own magnitude, then it gives you something known as the unit vector. Alright, it gives you something known as the unit vector. This unit vector will be in the same direction, alright? It will be in the same direction as your original vector. Let's say this is your A vector. Oh my god, really sorry. If this is your A vector, this will be known as your A cap. Alright, we denote it as cap. So this unit vector will be in the same direction, but it will have a magnitude of 1. That's why it's called a unit vector. Why does it have a magnitude of 1? It's pretty simple. I mean, let's say I have let's use this color now. Alright, so let's say I have 10x. Alright, or you know what, remove x, we don't like variables. Alright, so let's say we have 10. Alright, 10 what? 10 apples. Alright, we have 10 apples. Okay, we have 10 apples. Actually, this will go into permutation. I don't want that. I need something simpler. So, what can I really give you an example of? Okay. So, now, a vector. Okay. Can we write this as magnitude of the vector times direction? Alright, now listen to this an analogy and you will go crazy. Alright, not literally crazy, but you will love it. So when we talk about representation of vector in this arrow form, the length of this arrow gives you the magnitude. Alright, so how does this magnitude increase? How does this magnitude increase? How does the length of this arrow over here increase? To increase the length of this arrow, you need to multiply, right? You need to multiply its magnitude, right? You need to multiply something to its magnitude. Let's say I have a vector. So what's going to be 2a vector? It will be twice the magnitude. It will be twice as big. Okay, it's going to be twice as big. But let's remove that. Alright, it looks messy. Okay, so to reduce its size, can I divide? Just to reduce its size, can I divide? But what will I divide it with? What do I really want? I want the direction. I don't care about the magnitude, whatever may be the magnitude. I want the direction. So what I do is, as I said over there, that a vector divided by mod a vector gives you something called a cap, right, which talks about direction. Why? Right, why does it give you this? It's right over here. Because we said that a vector is represented in terms of magnitude as well as direction. Let's say I divide this by mod a vector. Similarly, I'll have to do that over here. Do you see it? I can cancel these two out and I get direction. But direction what? If I cut them out, it becomes 1. Do you get it now? Do you feel it? Because I cut these two out, alright, I divided them, I cut them. 10 by 10 is 1. 1 million by 1 million is 1. 1 trillion by 1 trillion is 1. Okay? So this is 1 times the direction. This is 1 times the direction. And since we called this vector to be unit vector, we can also see that over here it is 1 into direction, where 1 represents magnitude. Cool? We understood this, right? So now we understood the concept of unit vector very well, and that's why we are going to be using unit vectors to denote the direction of a particular vector. So now I'll tell you how you can express a vector using the coordinate system, and let's just go ahead and see what all do we have left. Alright, so we have addition of vector by components remaining, and then we have multiplication of vectors, and that's it, and then we'll be done. We will be doing the questions in the next video, in the next episode. In this episode we are just doing the theory. Alright, so now let's go ahead and learn about addition of vectors. Okay, wait, I am really sorry, we had to first talk about expressing a vector using the coordinate system. Alright, so now what I do is I'm bored of xy plane. Okay, I'm bored of xy plane, and I'm pretty sure you guys are bored of me, but I'm still going to irritate you for a little longer. So right, let me just erase this. Let me choose a better color. White looks a little more, classic. Alright, so let's say I have this right over here. This is your x axis. I'm bored of x and y axis. Now I want a z axis. Now I want a real space. Alright, volume as well. Now what I do over here is I take a vector and I do this. Okay, I don't know how to make this 3D. I don't know how to make this look 3D, but assume that this is coming outwards as well. Alright, let me try drawing it a little better. That became too flat. How about something like this? No, oh, okay, no, that's not working. How about something like this? No, I need to draw straighter. How about something like this? Okay, I think this is pretty fine. Alright, so actually let's do it with the two axes first. You'll understand the third axis by yourself. Alright, so now let's say we have a normal Cartesian plane. Even though I'm bored of x and y axis, I really have no other option. Alright, now let's say I draw a vector. Let's say I draw this beautiful vector over here, and the name of this vector is whatever your crush's name is. Then maybe you'll get excited. Alright, so how do I represent this in terms of the coordinate system? What I do is, first of all, I call this x-axis as I cap. I call the y-axis as j cap, and similarly I call the z-axis as k cap. Alright, why I, j and k? Because that's convention. That's all. I didn't decide it. If I decided it, I would have said A, B and C. I don't know why I, j and k, but that's why it is. Alright, so now how do we express these vectors in terms of this coordinate system? So I would like to give you guys should give it a shot and see if you guys can do it. I'll just take a sip of water. Alright, I know you guys didn't try. So, alright, okay. So how do we do it? What I do is break this into components. Very simple. Alright, again I'm going to take my torch. I'm going to shine it. And once I shine my torch, I see that this is the x component. Similarly, I take my torch over here. I shine it. This is supposed to be parallel, okay? Let's make the torch bigger. So it looks like this. Now, I'll check for its y component. And here is its y component. Okay? So now, let's call this x component as x, and let's call this y component as y. How do we represent this vector? Now what we do is we write this as this vector. Let's call this a vector. We write a vector is equal to x I cap plus y j cap. Do you get it? Do you understand it? Because we are expressing this in terms of I and j. I and j are in the direction of its components. Components should always be perpendicular. Alright, you can't really take just an arbitrary component. It should be perpendicular, but it can be anyway. So let me just give you an example. let's say I have a vector over here, and let's say I have this vector A vector. So either I can assume these two to be the components, or I can assume, just give me a second, or I can, I can assume something like this to be the component, or maybe something like this to be the component, or maybe something like this to be the component. You get it, right? So that's exactly how it works. They should always be mutually perpendicular. Doesn't matter on what axis you choose, I mean what orientation. So this is how we express any vector using the coordinate system. And similarly, if we have the z-axis as well, if we have this vector in a spatial plane, if it's coming outwards as well, then we express it as xi cap plus yj cap plus zk cap. Let's actually take a numerical example of this to understand this a little better. So let's say I have this graph over here. Alright, I'm just drawing this Cartesian plane so that it makes it easier for you guys to visualize. So now, oh my god, did you guys notice that this straight line over here is a free hand, and even this one, these two are free hands, so smooth. Alright, so okay, let me draw the vector over here. Let me call this vector, let me say that this is 30. Alright, now I'm going to project, and once I project, I see that this component over here is 12 units, and similarly when I project, I see that this component over here is 5 units. So now what I do is, first this is I cap, this is j cap. So I can write this as, let's call this A vector. Let's call this A vector. A vector is equal to 12 I cap plus 5 j cap. It's that simple. So we get it, right? Now we understand this. Now how do we add two vectors using the components? Let's say you're bored of the triangle law. I don't want to use the triangle law. I don't want to do it. Alright. What do we do then? So let's say I have two vectors again. Alright. I'm just bored of saying vectors over and over again. I'm pretty sure you guys are bored of hearing it. So let's say I have two vectors. They should be a little more, non-uniform. Let's use blue now. Let's see how blue looks. Okay, terrible. So let's say I have A vector over here, and let's say I have B vector over here. Now rather than doing that head, tail and all of that bullshit, we don't want to do that. Alright, we don't want to do that. We are smart people. Alright, what we are going to do is we're going to break A into components. Alright, let me just erase that. So how do we break A into components? Let's just assume any coordinate. Alright, for me I think this is the most simplistic, so I'm going to be assuming this. Alright, let's see this. Alright, how did I get this? I did this and then I did this. You get it, right? So this is the x component, this is the y component of A vector. Similarly for B vector, using the same orientation, you cannot go for another orientation for the components. You need to use the exact same one over here. In the beginning, let's say if I didn't choose the x and y to be like this, and if I chose them to be like this instead, then you would have to do the same thing over here as well. You can't change them for each individual one. Alright, so now let's say I chose this. Okay, that's the easiest one and it's the most intuitive one. Now let me remove this B vector over here. So I did, and I get this as the y component, this as the x component. This is the y component, this is the x component. Alright, let me call this, actually leave the dash. Let's call this x1, y1, x2, y2. Now we notice that x1 and y1, x1 and x2 are in opposite directions. So which one over here looks greater? Because we are only following, we are only checking for the arrow length to be the magnitude. So we can clearly see that x1 is greater than x2, alright? Now, what we write is x1 minus x2 I cap, because they are in the opposite direction, plus which one's greater? y1 minus y2 j cap is equal to a vector plus b vector. So do you guys understand this now? Alright, you guys get a good sense of it, right? You guys get a good feel of it, because breaking it into vectors makes this entire process a lot simpler, lot more intuitive as well. Now you guys can pretty much understand what's happening over here, right? So, right, now what else is remaining? Now we have scalar product and vector product remaining. So you guys understood how to add, and let's say if this x2 instead, let's go to the new slide, and let's say if they were in the same direction. Let's say we have this two vectors, we have a vector like this, and we have another b vector a little more inclined, right, little greater slope. Okay, right. So now I'm going to again break them into components. Now they're going to be in the same direction. Alright, so I'm going to call this x1, this is y1, this is x1. Similarly, I'm going to break this one as well. This is going to be, oh my god, that's not the x1. So this is going to be a little smaller. So x2, y2. So we can write x1 plus x2 I cap plus y1 plus y2 j cap is equal to a vector plus b vector, and that does it. So it's that simple. Using components is much more intuitive, and I always suggest this because sometimes formulas aren't as intuitive to us. I always love to use this method more. I mean, as long as if we talk about speed, I think once you have a good practice of it, this becomes way faster rather than doing it a square plus b squared is 2ab cos theta whole under root. So I think this is much faster and more intuitive. Right. So now we talk about the scalar product and the vector product. So now when we talk about multiplication of two vectors can be done in two particular ways. We have something called as, let's choose this one. Alright, so when we talk about multiplication of vectors, that can be done in two ways. One is known as the scalar product, and the other one is known as the vector product. Scalar product is also known as dot product. Vector product is also known as cross product. When we talk about dot product, okay, just give me a second. When we talk about dot product, how do we find the dot product between any two vectors? Let's say there's a vector and another b vector. Let's say I want to find a dot b. That is a mod a vector into mod b vector into cos theta. That is the definition of dot product. So have you guys ever heard of this? Like when we talk about work, right? When we talk about work in terms of physics, alright, not work that you're watching this video right now. So work in terms of physics, we have always said that whenever we apply a force perpendicular to the displacement, it comes out to be zero. Why does this happen? Because when we talk about work is actually, when we talk about work done, so work done is nothing but the dot product of force vector and displacement vector. and that's why when we evaluate this, we get mod f vector times mod s vector times cos 90 degrees. This theta over here is the angle between two vectors. I'll teach you how to find out the angle between two vectors also right now. So this cos 90, regardless of what these two are, we really don't care. This turns out to be 0, so this whole thing is 0. Alright, even if we don't understand it right now, but we will be learning about this when we reach work power and energy as well. Alright, so we have an interesting journey that's coming, and we are at 55 minutes and 30 seconds. Now, let me just stretch out for a second. Oh my god, what was that? No, that wasn't a bone. That wasn't a bone, that was my chair. Alright, so now, moving on, how do we calculate the angle between any two vectors? So this is also pretty simple. To calculate the angle between two vectors, let's say this and this. Now, what I do is I join them tail to tail. Alright, as I said, rearranging of vectors. Don't change the direction, don't change the magnitude. So if I move them parallel, let's say I have one vector like this, another vector like this. Let's say I move it parallel, and let's say I bring it over here. This angle over here is theta. Alright, now one common mistake that people do over here is they take a vector. Let's say we have one vector here, and let's say there's another vector. Now what they do is they join them head to tail, something like this, not like a little more inclined. They join them head to tail like this, and they say that this angle is theta. No, this isn't theta. This is 180 minus theta. Wait, what did I say? I'm really sorry. The angle between these two vectors will be 180 minus this theta. Why? Because, as I said, I will be explaining everything that I say. So now, let's say the angle between any two vectors, let's say these are two vectors, A vector, B vector. Alright. Now let's say I join them tail to tail. Let's first join them tail to tail first. Alright. I join them tail to tail. This angle is what? Theta 1. Let's assume it to be theta, or let's just assume this to be phi. Alright. We assume this to be phi. Now, let's say I shift this a little backward. Okay. That wouldn't bring a change in vector, right? That wouldn't bring any change in the vector. So let's say I shift it backwards and I bring it over here. Now that I bring it over here, let's say that this angle over here is theta. Alright, let's say this angle over here is theta. So what's the relation between this phi and theta? Can we write phi plus theta is equal to 180 degrees, because that's a straight line? And if we write that, let's take theta to this other side, we get phi is equal to 180 minus theta. So there's a proof to every single thing that I say over here. I won't ask you to, just mug up a thing for no reason. Everything over here will be explained properly. Alright. So now we move on to vector product. Alright, vector product or the cross product. But before we move on to vector product, the direction of A vector dot B vector, or if we talk about A vector dot B vector, this over here, this is known as the scalar product for a reason. Why? Because the product that we get from this, that itself is not a vector. Alright, we don't get a vector when we multiply, when we do dot product of two vectors. Alright, but when we do cross product of two vectors, so when we do cross product of two vectors, how do we represent cross product? If we have A vector, we write A cross B. Alright, this is known as A vector cross B vector. Alright, this is known as A vector cross B vector. When I do this, the resultant over here, the product of these two vectors, will be a vector itself. And it will be a vector such that it is mutually perpendicular to both of them. How? It will be mutually perpendicular to both of them only and only if it is out of the plane of the two vectors. What do I mean by out of the plane of the two vectors? let's say this is the plane in which the two vectors are lying, a and b vector. Let's say a vector is like this, let's say b vector is like this. Now the resultant of these two vectors, the product of these two vectors, will be coming out of the plane. Alright, so you can see over here that it is mutually perpendicular to both of them. It is mutually perpendicular to this a vector over here, and it is mutually perpendicular to this b vector as well. So now this over here, this is the product vector that will always be coming out of the plane in which the two initial vectors were lying, and that is why it is always mutually perpendicular to both of them. All right, now how do we calculate this cross product over here? Pretty simple again. So a cross b, a vector cross b vector, is actually equal to mod of a vector times mod of b vector times sine theta. This theta again is the angle between the two vectors, and remember the common misconception with angle, always make it tail to tail, and for triangle law, tail to head. Alright, or you can write a head to tail. Alright, that's a little simpler. Head to tail. Okay, this is the angle between the two vectors. Okay, so now we are completed with the whole chapter of vectors, the whole fundamentals of vectors. Every single thing that you will be needing from vectors has been properly completed. Let's go ahead and take a quick summary, and let me just go through the slides as well. So what did we initially begin with? We initially began with what exactly is a vector, what was the general term, why do we talk about, why do we say that a vector, when we were in younger classes, we were told that a vector is anything that has magnitude and a direction. And I forgot to give you this example over here. Now, since I said this, it has, I don't know if I gave it itself, I don't know if I gave it right now or not. I think I might be forgetting, but here's again. So we are told that in younger grades, we are told that vector is anything that has a magnitude and a direction, right? So when we talk about electric current, that moves from positive to negative. So that moves from positive to negative inside a wire. So it has a magnitude. It has a direction which is within the wire. Then why is this not a vector? Because now that we know what vector law of what the triangle law and parallelogram law is, we can actually make sense of it. But I think I didn't tell you the parallelogram law. I'm really sorry. It's a little scattered bit of information. So right, so let's talk about the parallelogram law. So when we talk about the parallelogram law, what we do is, this is probably the most useless law. Alright, I don't think you will ever need this. Okay, there are many things that is useless in this chapter as well that I have skipped, because there's something known as the Polygon Law. Alright, I'll tell you that also right now, because I really don't like when people have FOMO. Alright, I used to have that as well. When I saw a person not teaching every single thing, I would immediately close and I would go to another person. But no, I wanted teach every single thing. So let me just go ahead and do that. So when we talk about parallelogram law, what exactly happens over here? So what we do is, let's say we have a vector like this, and let's say we have another b vector like this. Now we arrange them tail to tail. Alright, actually let's make it easier. Alright, so let's say that this is the b vector. Now we arrange them tail to tail. So it's going to look something like this. Now, once you complete this parallelogram, the resultant of these two vectors, the resultant of a vector and b vector, will be along this diagonal. That's all. And that's why I said it is the most useless thing that you have learned today. The most useless. You'll never use it. I'm pretty sure about that. But again, let me give you another example. Let's say you have one vector over here. This is again a vector. Let's say another one, something like this, b vector. Join them tail to tail. Alright, don't do it head to tail, otherwise it will be wrong. Alright, so now complete the parallelogram. So it looks something like this, and the resultant of these two will be something like this. That's all. As I said, it's pretty useless. So yeah. Alright, so now we're going to be talking about the Polygon Law of vector addition as well, quickly, because I don't want any FOMO or anything. In the next session, we are going to be discussing, quite exceptional problems in vectors as well. So, right. But before that, let's finish this first. Alright, let me just tell you how many questions we're going to be doing in the next session. So, we begin from over here. Okay, so approximately 19 questions. Yeah, so approximately 19 questions will be done. Alright, cool. So, yeah, now let's talk about the Polygon Law of vector addition. Now, what we do over here is, let's say we have many of vectors, alright, many vectors arranged in some sort of the name itself suggests Polygon Law. What can it even be? So let's say we have something like this. Actually no, let's make it a little better. This, alright, so when you have a polygon of vectors, right? When vectors are arranged in polygon over here, what can we do? It's just multiple times. It's just using the triangle law multiple times. I'll show you how. Over here, what's going to be the resultant of these two vectors? The resultant of these two vectors using the triangle law would be this. So once we know the resultant, why do we care about these two vectors? Remove it. Now, what's the resultant of these two vectors? The resultant of these two vectors is this, right? So why do we care about this now? Remove it. Now what's the resultant of these two vectors? The resultant of those two vectors will be this one right over here. So once we have that, why do we care about this? Remove it. And similarly, what's going to be the resultant of these two over here? The resultant of these two over here is going to be this. Do you see it? It's going to be this and this. What's the resultant of these two vectors? Alright, what's the resultant of this vector and this vector? 0. Why? Because they have the same direction, opposite magnitude. Same direction, opposite magnitude. Cool? We understood it, right? So it's pretty simple. You can also understand it using another analogy. So since I drew this kind of a polygon, right, it doesn't matter what kind of a polygon it is. If it is coming back to the place where it started from, the what am I saying? Yeah, the resultant will be 0. And how can you take an example? Let's say I'm over here. Alright, let's say I go to my friend's house. Alright, I go to my friend's house, and from there I go to my girlfriend's house, and then from there I go to my other friend's house, and then from there I go to the playground, and from there I come back home. So what's my displacement? 0. It's as simple. Alright, vectors is one of the most simple, the most fundamental, and that's why it's taught at the very first. Now I don't want you guys to have any FOMO. Just let me know if there's anything that I missed throughout this video. Hopefully you like this first episode, and I'll be bringing up the problem session by tomorrow or maybe day after, and then we can have loads of practice, and hopefully you guys had fun as well. I'll see you guys in the next episode. Till then, goodbye.